So I'll introduce about the compliant mechanism. So what are compliant mechanism is that basically they are flexible mechanism that achieve force and motion transmission through elastic body deformation. That means they gain their motion from the relative flexibility rather than the rigid body joints. So mainly these are single piece structures or jointless structures. So these are the few examples of compliant mechanism. So what we can see common in all of them is that the absence of conventional pin joints. Instead, they have flexible connections that are known as flexures. So we'll understand their working in the next slide. That is the working of a compliant mechanism. We can compare both the mechanisms here. Both are the same mechanism in terms of their functioning. That is, they are basically gripper mechanism. So the one on the left hand side is a conventional mechanism, and on the right hand side is a compliant mechanism. So the only difference we see is that instead of conventional pin joints, there are flexures or thin sections that are used in a compliant version of the same mechanism. So we can see their working in the next slide in a short clip. So we can see that the same motion is achieved. The same motion is achieved by the bending of the flexures instead of pin joints. So what happens is that the bending of this flexure allows the rotation of the two links which they are means through which it is connected. So these are the means basically this is the comparison table between conventional and compliant mechanism. So in terms of friction, since there are no conventional joints, compliant mechanism have basically there is no friction and has an advantage over conventional mechanism. Same goes for the noise. Since there is no friction, no noise is present in this type of mechanism. Also precision, since these are jointless structures. So what happens is that due to wear and tear of the joints, the precision of the conventional mechanism reduces uh, as uh, as we use it for a longer duration. And for as for the part count, we have seen that the compliant mechanism can be found in a single piece only. Hence, very few part counts will be present in the compliant mechanism. Again, manufacturing cost, since there is almost little to no assembly, we get a very lower manufacturing cost in for the compliant version of the same mechanism. And in terms of simplicity, due to the presence of flexure, conventional mechanisms have an advantage over this, that they are simple to design, but compliant mechanisms are a bit complex in terms of design. So what is the problem definition is that we'll design a compliant bearing and obtain the following results at a defined load, that is maximum displacement, maximum von Mises stress, and minimum factor of safety of the mechanism. So this is the pseudo rigid body model of a cantilever beam. So first we understand what is a pseudo rigid body model. A pseudo rigid body model is basically it basically defines it basically defines a elastic member into its corresponding rigid body member. For example, in this slide, what we are saying is that a cantilever beam can be represented as two rigid body links connected through a torsional spring. So we'll see in the next slide the parameters that are used to convert this particular cantilever beam into its pseudo rigid body model. So what we get is the radius of the radius which with the tip of the beam beam's trace is given by 0.85 times the length of the beam, and also the corresponding torsional spring stiffness is given by 2.25 times the EI times L divided by L. Sorry. So where these E is the Young's modulus of the material of the beam, I is the cross-sectional area moment of inertia of the beam, L is the length of the cantilever beam, R is the radius of circular arc traced by the tip of the beam, and K is the torsional spring constant of the spring. So here are few assumptions that we need to make to design the this particular beam. So these assumptions are made for the simplicity of the design, and these can vary depending upon the application of the mechanism. So the first parameter is that the required angle of rotation is 15 degrees with an actuation torque of 500 Newton mm, and the total number of beams selected is 4, and the cross sectional area of beam selected is circular, and length of the beam selected is 120 mm, and the material of construction is selected ABS, since for the ease of since it is easily available for 3D printing. So this is the final design which we get. So I'll talk about this design. What happens is that we can see that the beam is inserted into a cavity. So the reason to do so that is to align the center of rotation of each of the beam through the axis of shaft. We can see that. Uh, so this particular design is modeled in Inventor and simulated in Inventor. And again, ABS is chosen as the material of construction. And for this particular case, we have applied an intermediate torque of 150 Newton mm. So these are the results which we obtained. That is the total displacement. The maximum displacement is 6.8 mm. At the corner of the cube, and again the this is the x displacement, which is maximum of 4.81 mm at the corner of the cube. And this plot basically gives the von Mises stress, since we it is not visible here, since the maximum von Mises stress is developed at the base of the cantilever beam. So the pointer shows that it is basically inside the slot. So the design summary is that the maximum von Mises stress induced was 12.5 MPa, and which was well within the limits, and the minimum factor of safety was 1.57. And from the displacement plot, angle of rotation was achieved was 7 degrees. So in conclusion, following are the various parameters that can affect the design of band bearing. That is the number of cantilever beam elements selected, shape of the base to which the shaft is attached, cross section of the cantilever beam element selected, length of the cantilever beam element selected, and the material of the cantilever beam element selected. So basically these parameters affect the design of the compliant bearing. So what can be done in future is that a physical model of the design presented can be manufactured and tested, and a comparison between the real model and simulated model can be done. And lastly, various versions of the model can be designed and tested as discussed previously. So these
Everyone, my name is Anjali Singh from Indira Gandhi Delhi Technical University. So today I'll be presenting our paper. The topic is investigating the relationship between sleep composite and mental and physical health. So let's start with the problem statement that why we choose this topic. So as we all know, getting enough sleep at the right time is the key for the physical and psychological well-being. There are various health problems related to sleep disorder and medical research and sleep disorder according to the data collected by the World Health Organization and Medical Research Center. Therefore, it becomes important to understand the sleep cycle and how it can affect our daily routine. So, the goal was to predict mental and physical health in people using healthcare data using machine learning models. So, for the scope of this project, we have predicted heart disease to determine physical health and depression and anxiety to determine mental health. So, the data is originate from National Health and Nutrition Examination Survey conducted by the Centers of Disease Prevention. So the data was gathered between 2005 and the year 2018 with 36,295 entries from the US citizen. The only data that was remained consistent over the time was used. So the questionnaire is consisted of 10 questions and depression is thus defined in a score of 10 or greater. The 10th question of the survey was dropped since it wasn't involved in the adding of the score. So the cleaning process includes adding up the score for the 9 questions and then marking entries as depressed or not depressed based on greater or equal to 10 threshold. So then the data is pre-processed by removing all null and ambiguous entries, feature engineering, filling missing values, and scaling. with the purpose of boosting model accuracy. All the columns were renamed for readability, missing values were filled as missing or zero, and the data was split into training and testing in the ratio of 70 to 30. For the data visualization, we visualize the data by plotting x-axis as trouble sleeping history against count depression, in which we can see those who have trouble sleeping have 4 times the percentage of depression than those who don't. Similarly, we plot trouble sleeping history against heart disease, in which those with a trouble sleeping history have 2 times the percentage of heart disease than those who don't. For the model preparation, we have used one-hot encoding, which is a technique that we use to represent categorical values as numerical values in a machine learning model. And the second method is scaling. The quantile transformer will be used for scaling the data as there are some numerical columns with far outliers. This method transforms the features to follow a uniform or a normal distribution. And last, we used one K-means clustering. We use Klinsky-Harbaugh's index, Silhouette coefficient, and inertia index of K-mean clustering to determine the value of K. With this 6 seemed like an appropriate cluster number as there is a bump in the Silhouette score there. The approach for this project was to create many different model types to see what performed the best and to compare and contrast the different types of model. We compare the performances of logistic regression, XGBoost, and random forest classifier. Models were evaluated using a classification report, a confusion matrix, and an ROC-AUC curve. For the result, the first experiment various classifier to compare the accuracy of our model, such as logistic regression, K-neighbor classifier, support vector classifier, and many more. The dataset is tough overall, as seen by the classification accuracy ranges of 50.5% to 94.34% for the heart disease and sleep relation, and 44.45% to 99.47% for the depression sleep relation. For the second experiment, we also included various data pre-processing steps and models preparation to investigate the improvement in accuracy from the first experiment. We also employed several assessment criteria, including precision recall and F1 score to find out the accuracy. The accuracy varies from 79 to 91% for the depression and sleep analysis, and from 99 to 99.99% for the heart and sleep analysis. So there are some future scope for this project, as first can be making application for user. So the main aim for this future implementation can be to expand the research will be to make an application to categorize the users as depressed or not depressed, or whether that user has heart disease or not. Also with that, we can suggest users some precautions and method. The second direction could be add more entries and evaluate valuable features by finding the right balance between acceptable amount of error and amount of data needed to have an accurate model is definitely easier said than done. Finding a way to add more patient entries may also be valuable. And the last parameter can be by testing more parameters, that the depressed and heart disease class was so difficult to classify that perhaps a different scoring metrics can be treated, like maximizing just for recall or weighting recall even more heavily in a custom F static scoring object. Thank you.
I am Mansh Jadeja, and I am an undergrad student at Delhi Technological University, and I'll be presenting my paper titled Speed Discipline for Autonomous Vehicles in Indian Driving Conditions. So the abstract of the paper is that one of the major challenges that autonomous vehicles face is the ability to adapt to different driving conditions. So currently, all the research that has been done for autonomous driving models have been focused in current markets, but there has been no model for Indian driving discipline. And in that case, we are trying to propose a model and some data with this research. The autonomous vehicle must be able to detect and respond to objects in real time, estimate the distance to the object, and predict the optimum speed at which it should move to avoid collisions. To achieve this, a state-of-art object detection algorithm using YOLO version 7 has been used to predict the optimum speed at which a vehicle should move. The proposed methodology involves the use of YOLO version 7 model for object detection and speed prediction for autonomous vehicles. So we are obtaining a video feed from a camera and identifying and classifying an object into different classes and determining if the class already exists or is that a new class. So based upon that, if the class already exists, we start storing the images for the object, and that image also and using the camera and focal length from that camera, we also calculate the distance of the object from our current from the camera, and using the timestamp for that particular class that we have stored, we can calculate the distance and time, and using that we can calculate speed. So this simple model has been proposed, and for that we have used YOLO version 7. So the speed prediction is then used to control the speed of the autonomous vehicle to prevent collisions. The design of the model has been proposed, and two parts that as I have explained, object detection and object distance. These are the two parts of the model. This is a little explanation for the YOLO model. You only look once is a popular algorithm because it achieves high accuracy while also being able to run in real time. The algorithm only looks once at the image in the sense that it requires only one forward propagation pass through the network to make predictions. After non-max separation, it is then outputs recognized objects together with the bounding boxes. This is the explanation. This is the representation of the data that the model outputs, and that has internally. And we are on at the output. We are only getting the distance, as we can see in the image, that the model detects that there are different objects of different classes, and represents the data distance of the each object, and the closest vehicle that it identifies as a car, and it has represented a distance of 270.84 inches. Related work that has been done on the model, that there has been extensive research on object detection algorithms for autonomous driving applications. YOLO is a single stage detection algorithm that can detect objects in an image with high accuracy and speed. There has also been research on using machine learning algorithms for prediction and autonomous driving. One approach is to use regression models to predict the speed of the vehicle in front based on features such as distance, relative velocity, and acceleration. However, these models may not capture the complex relationship between the features and speed, leading to suboptimal performance. So the R model overcomes these fallacies, as the model classifies the object into different classes and then calculates the speed of the nearest object, or the object that is most likely to cause collision. This is an object distance estimation, that how the YOLO creates a frame and how it identifies and how it creates a single frame for each object. So we measure the width of the object in question. We then capture the reference image and specify the actual distance for the said reference image. Multiple reference images together form the reference class for an object. These classes are then utilized along with a model trained on YOLO4 tiny weights to provide the object's distance in front of the camera. For distance estimation, a reference image is fed to the model with the distance constraint specified. Then the algorithm calculates the distance using the focal length and various functional arguments. We have also done some experimental results and calculated errors in our model. So for testing the data, we took the distance of randomly placed objects in a field of around 6 meters, as that our current driving conditions allow us to maintain only so much distance with the car in front of us. These objects were from the classes that the model could identify. We only use the YOLO model to take images and calculate the distance of those objects over 20 data points. The same was done by using the ultrasonic distance sensor to establish the ground truth, but that will not be part of the future model. The distance from the UDS is the actual distance, and the distance from the YOLO model is the calculated distance. From the collected data, we plotted the graphs to assess the trends. So graphs for two ranges, error percentages have been presented in this PPT for 100 centimeter, 200 centimeter, 200 centimeter, 300 centimeter. And these are the actual data, the actual errors and percentages error. And as we can observe, as the distance increases from the data point, the error also increases. And the same has been observed in the range from 2 meter to 3 meter. So, and Kong and clusterized graph for ranges 1 to 6 meter has also been plotted, and the average percentage error is 8.68% in this range. There are we had also tested for 1,000 images for object classification as well. So these are the root mean square errors and average F1 score for the image classification. This is for the distance and this is for distance estimation, and this is for speed estimation. Overall, the experimental results demonstrate that our proposed system can accurately detect objects, estimate their distance from the camera, and predict the optimum speed for safe autonomous driving. So in future scope, we have proposed that we can develop a better interface for our model, because currently a lot of images and lot of things are presented in a very clustered manner. So in that we have included in a future scope, and these are the references from using which we have studied and performed use YOLO V7.